Hello and welcome back to the video for lesson 3.7. This lesson is all about rational functions, and we only work on this in one lesson, but it's all about, when I say rational functions, I mean a number that is, can be in the form that's an equal sign of a polynomial in the numerator and a polynomial in the denominator. So they're two separate polynomials. Where h of x is not the constant zero function. So we can't have a zero in the denominator or it would be undefined. So it says, what is the domain of 1 over x? This would be our basic rational function. So if you think about it, as x gets really, really big, as x gets infinitely large to infinity, let's say we go from 1 over 1 to 1 over 10 to 1 over 100 to 1 over 1,000 to 1 over 10,000. This gets really, really, y is going to get really, really close to 0, right? And x can't equal 0, so it can't do anything here. So it's going to go from really big, it's going to get really, really small here. And then, it's going to look something similar as x goes 1 over a negative 1. It's a negative 1, and then it's going to go to a negative 1/10 if this is negative, and then to a negative 1/100th, and then a negative 1,000th. And so it's going to get really, really small. Oh, no. It's going to be at, a negative 1 will be a negative 1. And then it's going to get really small that way. Sorry about that. So it's going to look something like this. Let's look at it in Desmos. So the basic rational function is this that I just showed you here. We can zoom in a little bit. So you can see at 1, it's negative 1. And that positive 1, it's 1. Okay, so that's our one limitation is the denominator. And we're going to call this the large small principle. As the denominator gets large, the overall value gets small. As the denominator gets small, the overall value gets large. So you could see from the picture, there's something called an asymptote. And we call an asymptote where the output gets really, really close to it, but could never get there here. And it's actually the x is getting really, really close to 0 from both directions, but it can never actually be 0 because it would cause an undefined value. And that's when x is equal to 0. Okay, so that's called an asymptote. So we have vertical asymptote and horizontal asymptote. To find the vertical asymptote of a rational function, first make sure that p and q have no common factors. Then the vertical asymptotes occur at values of x where q of x, or the denominator, equals 0. At these values of x, the function values will approach positive or negative infinity. So the initial one that we looked at here has a vertical asymptote. We say it's a VA at x equal to 0. That's when our denominator equals 0. So let's look at example 2. So the vertical asymptotes here, we're only looking at the factors of the denominator. So that's going to factor into the difference of the conjugates x minus 3 and x plus 3, which are not in common with any factors of the numerator. So we're just going to set them each equal to 0. And find out we have vertical asymptotes at x equal to 3 and x equal to negative 3. And let's check that one out in Desmos 2. It's good to be able to look at these. And that's this one right here. 3x over x squared minus 9. So you can see there's one here. You can't see it, but you can tell it gets really, really close here. And if we did a line at x equal to a -3, you could see that's where it's getting really close. You could see that's where the asymptote is. And then 1 at x equal to 3, you can see those asymptotes. And I'm going to change the color here. By going up to here, and I'm going to change that to orange just so we can see. So you can see there are the two asymptotes, and I'm going to zoom out a little bit so you can see them. So that's one way to kind of look at it. The end behavior and horizontal asymptotes of a rational function, or something else we need to look at. So we've looked at the vertical asymptotes. So if we have our polynomial P over the polynomial Q, then we have the leading term on each. So the highest degree on each, and the highest degree on the numerator is going to be N, and the highest degree on the denominator is going to be M. So if the numerator is smaller than the denominator, it's going to approach 0. We've already kind of talked about that. And so that means there's a horizontal asymptote at y equals 0. Okay, and that's if n is less than m. If they're equal, so if they're growing at the same rate, then we're just going to be looking at the coefficients. So there's going to be a vertical s or a horizontal asymptote at y equal to the leading coefficient of p over the leading coefficient of q. So a over b. That's where it would be, only if the degrees are the same. And then if the numerator degree is bigger than the denominator, if the numerator is growing at a faster rate than the denominator, then there's not going to be a horizontal asymptote. So there's 3 possibilities. Let's write that. 3 possibilities. Okay. It says find the horizontal asymptote of the function here. So we can see that n is equal to 1 and m is equal to 2. N is the degree on the numerator and m is the degree on the denominator. N is less than m. So that means that we have a horizontal asymptote at y equals 0 because the denominator is growing quicker than the numerator. It's the large, small concept. Okay, graphing rational functions is important, but I know that you can do that in Desmos, and I'm going to keep showing you all that in Desmos. So it's kind of having us find the vertical asymptote, the horizontal asymptote, and the x and y intercepts, and then that kind of is going to help us graph it by hand. So I'm going to walk you through that, but we're going to definitely put them into Desmos as well. And you can see that Desmos link in Canvas. So it says, let's sketch the graph. So let's find the y-intercept. That's always the easiest one. It's when x is 0. So when x is 0, we get a -1. So let's just put f of 0. We get 0 minus 1 over 3 times 0 plus 1. So that leaves us with a -1 over 1 or -1. Okay, so there's 1 point. So 0 and a -1. Okay. And then we can see that n is equal to 1 and m is equal to 1. So that means because they're equal, then we have a horizontal asymptote at y equal to a over b, which in this case is just 1 over 1 or 1. So we have a horizontal asymptote at 1, at y equal to 1. So I'm going to draw that there. And then our vertical asymptote is where the denominator is factored. So that's just 3x plus 1 equals 0. That's at a -1/3. So at x is a -1/3, we have a vertical asymptote here. Okay. And we know there's a point down here, so they're going to be opposite of each other. Kitty corner here. And then our x-intercepts are where's the function is equal to 0. So that's just our numerator because the denominator won't matter. So it's where our numerator is equal to 0. So x is equal to 1. So there is 1. So at 1 and 0. So it looks like we have something going on like this, and then we're going to have something going on like this. So let's validate that in Desmos. And it's up here. Oh, just what we thought. And we can just go down here and put in that vertical asymptote. We think there's one at a negative 1/3. And we could change the color, but you can see that that does match what we thought. Okay, what about example 5? Let's sketch this graph. Okay, so we're gonna again find our y-intercept, which is f of 0. So that's 3 times 0 is 0 over 0 squared minus 9 is minus 9. So it's at 0. So 0, 0. We have a point there. Okay. And our vertical asymptotes are only when the factored spots of the denominator. So that's going to be the x equal to 3 and x equal to a negative 3. Like we did on this one. Because essentially we're graphing what we did on this one. It's the same function. Okay, so we have a 3 and a negative 3. Okay. And then our horizontal asymptotes are going to be, let's see, n is equal to 1. That's the highest degree on the numerator, and then m is equal to 2. So it looks like we have it at y equals 0. Oh, that's interesting, right? Because we have a y-intercept at 0. But it looks like we can't actually equal 0 here. So that is interesting there. Let's see, and then our x-intercepts is when the numerator is equal to 0, which is when x is equal to 0. So 0, 0. So let's just go ahead and look at this in the graph in Desmos. We've already looked at that one. So it looks like it cut through there, and that's pretty cool. But I did have a horizontal asymptote at y equals 0. So it has one going on here, but then this does cut through. So the asymptote there is only when it's less than this number and greater than 3, less than 3 and greater than 3. Very cool. Okay. So there is one third type of asymptote that we could possibly have, and that's called a slant asymptote, and it only happens in a quirky situation. So if the degree of the numerator of a rational function is 1 greater than the degree of the denominator, the graph of the function will have what is known as a slant asymptote. So when we went through the definition, we said there's 3 possibilities. You could have the numerator is less than the denominator, so it goes to 0, or that they equal, or if n is bigger than m. There's no horizontal asymptote. But if n is bigger than m by 1, right here, by 1, then we have the slant asymptote. So in that case, we would divide p divided by q, and the remainder is a linear equation, and that's the slant asymptote. So it's the remainder. Okay, so let's find what we're gonna fix. It's like find the slant asymptote, and we can see that n is equal to 2 and m is equal to 1, and 2 minus 1 is 1. So we know there's a slant asymptote. So if x minus 5 is divided into here, I'm going to use synthetic division. So that means I'm putting 5 over here because c is equal to 5 for synthetic division. And my coefficients are 1, a -3, and a -4. So I'm bringing down my 1. I have 5 times 1 is 5, and I add them and I get 2. And then 5 times 2 is 10, and I add them and I get 6. And my remainder is just 6. Because I've got x plus 2. So, the s of x is the remainder, and it's just y equal to 6. So, I have a slant at y equals 6. Let's put this one into Desmos. Here I have it, x squared minus 3x right here. So you can see if I put in the equation down here of y equals 6, you can see it there. Oh, it's actually the x plus 2. 6 is the remainder, but it's a linear equation, is when you divide, it's what's left over. The x plus 2, pardon me. Let me go back there. So the x plus 2, the remainder is what's left over, the s of x, that is true. But the asymptote is at the y equals ax plus b that factors, that divides out. And that's what we had here, was the x plus 2 that was left, that was divided out. So there is my slant asymptote at x plus 2. Okay. Example 7 says sketch the complete graph. Okay, so we've looked at these. Let's see what we can learn from here. So if we look at f of 0, we can find the y-intercept. We have a -3 over 6 is a -1/2. And so that's 0 and -1/2. And then my x-intercept is my numerator. X minus 3 equal to 0 is x equal to 3. So 3 comma 0. And then look, I've got 1, 2, 3. There's a point. And then 0, -1/2. There's 1. And then my vertical asymptote is going to be my denominator factored. So x squared minus 5x plus 6. I can factor that into x minus 2, x minus 3. So I have vertical asymptotes at x equal to 2 and x equal to 3. And this is at 3, 0. Okay, so that is into and then my horizontal asymptote is because n is equal to 1 and m is equal to 2, and it's less than, then I have a horizontal asymptote at y equal to 0. So it looks like I have something going on here, and then there's going to be something in between there, and then there'll be something here. So let's just go look at it. For the most part, I want you to be able to pull out these things, but to be able to see it in Desmos, which is this one right here. Oh. And so there is, oh, I forgot to point out one. Let me go back. I had to point out one thing. And the vertical asymptotes, if they share a factor, the factor doesn't count as an asymptote. So x minus 3 on top is a factor of x minus 3. So that asymptote doesn't count. So there's only the asymptote at x equal to 2. So the x equal to 3 doesn't matter. Let me go back and point that out here. So I'm going to put that at x equal to 2 and let you see that. So you can see that asymptote there, and then the horizontal one at 0. Cool. Then the last problem is an application. It says, what is the average cost per mile per day if the daily cost of renting a car with unlimited mileage is $50? So I guess you can look at days and costs. So if you want one day, it's going to cost $50 per mile per day. If you went, oh, and per day you went 1 mile. So this is really miles per day that you're driving. If you drove 10 miles per day, then it's going to be 50 divided by 10, right? Or $5 per mile. If you went 100 miles per day, then it's only 50 cents per mile. So that goes down. So it looks like my equation is an inverse equation, an indirect, because it's 50 divided by x. And that's what they're looking for. And that wraps up chapter 3. Catch me back for some review videos.